Question number 9 is from Ray Optics. It says there is a block of refractive index 2.72 and height is 10 millimeter, and here is a liquid. A point source is kept at the center, obviously at the bottom of the block, and it says it is found that light emerging from the block to liquid forms a circular bright spot of diameter 11.54 millimeter. That means radius is 5.77 millimeter on the top of the block, and we have to find mu of the liquid. Quite obviously it goes in this way, denser to rarer, the light would emerge till the critical point, and this is the radius. This is theta, and this angle is also theta, more precisely the critical angle, and the first thing is sine theta c is 1 by mu, but this time mu of denser by rarer, the mu of liquid. That's equation number 1, and equation number 2 is sine theta c will be equals to 1 by 2. That's very easily found out, because given this value and this tan theta, if you calculate, is r by this height, that leads to theta equals to 30 degree. So based on these two, we could easily go for option number C. Now let's see question number 10. Question number 10. A tennis ball is dropped on a horizontal smooth surface and it bounces back to the original position. That means the collision here is elastic. The force on the ball during the collision is proportional to the length of compression. It means during collision, the force is directly proportional to the degree of compression. And we got to see the best graph of K versus T. You could see here that while it falls down, velocity increases linearly with time. That means kinetic energy has to go parabolically. So we could straightway eliminate A and D. Now this is during the flight, 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 parabolically. And when it is in contact with the ground, again you could see the force is directly proportional to x. That means velocity will vary by x square, because you integrate this, and kinetic energy x raised to the power 4. So it has to go in a curve. This is how kinetic energy changes during the collision, while option number C says kinetic energy is constant during the collision. The option would be ruled out. So the correct option would be option number B. Now we'll go to the next section, which begins from question number 11. This is quite a good question, question number 11 and 12. PQ and RS are two long current carrying wires, and these two will carry current I and I. The direction has not been given. And this one carries current I as seen anti-clockwise from the top, and the distances are given. 11th question says when D is almost equals to A is the radius of the ring. That means this almost comes here, but wires are not touching. That means these two wires are very, very close, but they haven't touched yet. The magnetic field on the axis is 0 at a height h above. Then we need to fix up the direction of current in the wires as well as the value of h. Quite obviously, if you want to see the direction, you can handle it logically. The current is this, so the field would be outward. And at the axis, if you want to nullify the field, the field due to PQ and RS has to be in the inward direction, and that can be done by PQSR, you could say. So in this it will be from P to Q, and in this it will be from S to R. So either option number B or C is valid. Then comes the direction. An imagination is required. At a given height, we have to find the field due to this and this. It would be easier if you see from this side. You would be seeing what is the direction we have seen from P to Q and from S to R. So P to Q would be cross and S to R would be dot if you see from this side, PQSR. Then at a height h, so from this, at a height h we got to calculate. I changed the view. At a height h we saw from this side. And quite obviously this is A, this is A. Let's find the net field here. Due to this, the field would be in this direction, and even due to this, the field would be in this direction, and the resultant would be down. And if you see from this side, the field due to this and this has to be down to nullify the field due to the ring. So let's see the resultant field due to this and this. That would be, first of all, the field here is mu naught I by 2 pi distance a square plus h square. And the downward component, if I call this angle as theta, you could see this angle would also be theta. So its cos component and even its cos component would be down. So 2 cos theta would be a by root a square plus h square. That's a net field down due to this, and that has to be exactly nullified by the field due to the ring mu naught I a square by 2 a square plus h square 3 by 2. And it's a very simple calculation. H is almost equal to 1.2a, so this will give us option number C. For the same figure, we'll see question number 12. Let's go with question number 12. It says this D is much greater than A, and the loop is rotated about its dia parallel to the wire by 30 degree. So here, parallel to this by 30 degree. That means the loop is rotated in this way. If current in the wires are in opposite direction, that means the field due to these at the center would be added up. We want the torque in the loop. So first, let's calculate the net field. That's mu naught I by 2 pi d is the field due to one, due to other multiplied by 2. And the torque will be mb sine 30, where m is pi I a square, b sine 30 is half. And this calculation will lead to option number B. Now we'll go to question number 13 and 14.